Good afternoon, everyone. I'm Manisha Ronyal. I'm doing my PhD at South Dakota State University, and I'm going to present on diesel generator model development and validation using moving horizon estimation. In more than 300 communities in Alaska and Canada, distributed diesel generators are usually the primary source of electric energy due to their low investment cost. However, in future, the diesel generators are more likely to be integrated with the renewable in water-based generation, such as photovoltaic and the wind. This reduces the reliance on the imported diesel fuel and the energy price in one hand. However, in the other hand, it introduces more faster and stochastic dynamics. Thus, it becomes crucial to understand the dynamic response of the diesel-backed microgrids for accurate modeling of the power system components. The parameters in the inverter-based microgrids are time-varying, thus it becomes equally important to implement an online estimation technique for the system stability and the adaptive system control. So the main objective of this work is to develop the simplified linear model to simulate the frequency dynamics of the detailed diesel plant and employ an estimation technique to provide the online estimates of the unknown set of parameters of the simplified model. In section 2, we can see the simplified block diagram of the DC system under study, and the dynamics of the system are modeled using the swing equation and the differential equation. The system contains a synchronous generator and the isochronous governor that provides the approximate model to represent the frequency dynamics. The exciters and the voltage regulators are neglected in this work because they have faster response than the frequency dynamics. The simplified governor is represented by single time constant Tc and the governor gain K, whereas the inertia M and damping constant D represents the generator dynamics. With these assumptions made on deriving the approximated model, the estimator reduces the computational cost and provides a quick convergence. In section 3, we can see the detailed simulation setup of the diesel sensors system. The DC models of governor and the synchronous machine are used from the standard library in MATLAB Simulink. The power division signal is a square wave signal here that provides the various step changes in active power. The resulting frequency changes are measured using the phase lock loop, that is PLL. Because the online measurements of frequency are more likely to contain noise in the real system, additional noise, that is non-Gaussian noise, is added to the input measurements to make it more realistic. A horizon length of 700 is chosen to capture the 2.1 seconds of the excitation signal. The sampling time of MHA is 0.003 seconds, that is selected based on the larger real part of the eigenvalue from the system matrix. In section 4, we can see the results of the estimates, that is for the state and the parameters. MHC estimates the frequency and the input power supplied by the generator at the same time as shown in this figure. Also, it converges within a short time period of 2.1 seconds. The accuracy in the estimations are now illustrated by calculating the normalized root mean square value that is found to be less than 5%, and that is an acceptable range for the power system dynamic studies and the controller design. The average estimates of the parameters are represented by the yellow dashed line in the kernel density plots and the histogram distribution plots. MHC tries to achieve a minimum cost function defined over a finite horizon length. However, the cost function does not reach the value 0 due to the noise in the measurements. In section 4b, MHC works well in estimating the state and parameters with small error. However, it is important to validate the estimated parameters to check how accurately it captures the frequency response in comparison with the detailed model. Thus, this can be achieved by using the estimated parameters back in the simplified model, and we can see the frequency response from the simplified model is very much close with the detailed simulation setup. Thus, it is accurate enough for the future application in the predictive controller design. In conclusion, the proposed approach provides the online estimation of all parameters for the given nonlinear problem with constraints on the model estimates. The developed simplified models now can be applicable to accurate modeling and the proper controller design of the renewable integrated diesel generator system with time-varying parameters. I would like to thank US Department of Energy and the STSU Joint Group of Research for supporting this work. Thank you.